Dynamic positioning, or DP, is a complex science. It allows a vessel to hold its position and heading automatically. The system achieves this by using thrusters to counteract environmental forces like wind, waves, and current. The total output from all these thrusters working together is what we call the DP force. It is not the push from a single bow thruster or a single propeller. Instead, it is the net, combined force generated by every thruster online at that moment. This force is carefully managed by the DP control system to keep the vessel exactly where it needs to be, pushing against nature with just the right amount of power. Imagine a vessel being pushed from the side by a strong current. The DP system will engage thrusters on the opposite side to push back. The DP force is the sum of this counteracting push. It is a vector, meaning it has both a direction and a magnitude. The direction shows which way the thrusters are pushing, and the magnitude shows how hard they are pushing. The goal is to create a DP force that is equal in strength but opposite in direction to the environmental forces. This creates a state of equilibrium where the vessel remains stationary over a fixed point on the seabed, even in challenging weather conditions. A common mistake is to think of each thruster working in isolation. This is incorrect. The DP system orchestrates them like a team. It might use two bow thrusters pushing to starboard and an azimuthing stern thruster pushing slightly to port to achieve a very specific resultant force. This resultant force is the DP force. It is the final, calculated output that matters. The system continuously adjusts the power and angle of each thruster to maintain this precise combined force. This coordination is essential for the stability and accuracy of the entire DP operation, ensuring no single thruster is overloaded while the vessel holds its ground. This concept of a combined force is fundamental to understanding how a DP vessel operates. The operator on the bridge does not command each thruster individually. Instead, they command the DP system, which then calculates the most efficient way to generate the required DP force. It considers fuel consumption, wear and tear on machinery, and the risk of ventilation. The result is a finely tuned, responsive system that can hold a multi-thousand-ton vessel in position with remarkable precision, all thanks to the clever management of this single powerful concept, the DP force. The dynamic positioning control system is the brain of the operation. It works tirelessly, performing complex calculations every second. Its primary job is to determine the exact DP force needed to keep the vessel on station. To do this, it relies on a constant stream of information from a wide array of sensors. Wind sensors measure the speed and direction of the wind. Motion reference units, or MRUs, measure the vessel's roll, pitch, and heave. Gyro compasses provide heading information. And most critically, position reference systems like DGPS or acoustic transponders tell the system precisely where the vessel is located. Once the DP system gathers all this data, it builds what is known as a mathematical model of the vessel. This model understands how the vessel will react to external forces. For example, it knows how much a 30-knot wind on the beam will push the vessel sideways. By comparing the vessel's actual position to its desired set point, the system calculates the total environmental force acting upon it. It then computes the necessary DP force and equal and opposite reaction that the thrusters must generate to counteract these environmental forces and nullify any position error. This calculation is not a one-time event. It is a continuous loop of measuring, calculating, and correcting. The DP system displays this information clearly for the operator. On the DP screen, the DP force is often shown as a graphical vector, an arrow originating from the center of the vessel graphic. The length of the arrow indicates the magnitude of the force, usually shown as a percentage of the total available power. The direction of the arrow shows the direction in which the combined thrust is being applied. For instance, if the arrow points directly forward, it means the majority of the thruster power is being used to push the vessel ahead. This visual representation allows the DPO to understand the operational state at a single glance. This real-time calculation and display are what make DP operations possible. The system doesn't just react, it anticipates. Based on the data trends, it can predict changes in environmental forces and adjust the DP force proactively. If the wind sensor shows a gust is building, the system will begin to ramp up thruster power before the vessel is pushed off its station. This predictive capability, combined with its powerful computational core, ensures that the DP force is always appropriate for the conditions, providing a stable and reliable platform for complex offshore tasks. Every vessel turns around a specific, often invisible point. This is called the pivot point. It is the center of rotation. When you turn the wheel of a car, the car pivots around its rear axle. For a ship, this point is not fixed. Its location changes depending on how the vessel is moving and the forces acting upon it. Understanding the location of the pivot point is absolutely critical for safe and precise maneuvering, especially when working close to structures. A DPO who does not know where their pivot point is located is a danger to the operation. When a vessel is completely at rest in calm water with no headway or sternway, the pivot point is typically located near its longitudinal center, around the midships area. If you apply a turning force, like a bow thruster, the bow will swing one way and the stern will swing the other, rotating around this central point. However, the moment the vessel starts moving, this changes dramatically. When moving ahead, the pivot point shifts forward. It can move as far as 1/4 of the vessel's length from the bow. This means the stern will have a much larger swing than the bow during a turn. Conversely, when the vessel is moving astern, the pivot point shifts aft. It moves towards the stern of the vessel. Now, when a turn is initiated, it is the bow that will have the much wider swinging arc. During DP station keeping, the situation is more complex. The DP system uses thrusters at both the bow and stern to control heading. This action effectively pins the pivot point close to the vessel's center of gravity, which is often also near the location of the position reference system antennas. This allows the DP system to make heading changes with minimal change in the vessel's position, which is essential for station keeping. Knowing the pivot point's location is vital for safety. Imagine a DP vessel working alongside a platform. The DGPS antennas, which provide the primary position reference, are located on the bridge. The DP system will try to keep these antennas perfectly on station. By using both forward and aft thrusters, it effectively makes the pivot point coincide with the antennas. This ensures that when the DP system corrects the heading, the vessel turns on the spot without the stern or bow swinging out and hitting the platform. This is a key principle of safe DP operations. A skilled dynamic positioning operator, or DPO, must do more than just watch a screen. They must develop a deep practical understanding of their vessel and its systems. The first step is to thoroughly understand the vessel's layout. A DPO must know the exact location of every thruster, every position reference sensor antenna, and every wind sensor. This knowledge provides context to the data displayed on the DP screen. Knowing that the DGPS antennas are on the forward mast helps the DPO visualize why the system holds that specific point and how the rest of the vessel will behave around it. Monitoring the DP force vector is a core task. The DPO should constantly observe the direction and magnitude of this force. A sudden increase in the force percentage indicates a change in environmental conditions or a potential problem. A rapidly swinging vector might suggest confused sensor data or an unstable system. By interpreting this visual cue, a DPO can anticipate issues before they become critical. For example, if the DP force is consistently high, the DPO knows the vessel is working near its operational limits and must be ready to take action if conditions worsen. Interpreting sensor data correctly is another crucial skill. The DPO must not blindly trust the system. They need to cross-check information from different position reference systems. If two DGPS units show different positions, which one is correct? The DPO must be able to analyze the quality indicators for each sensor and decide which data to reject. This is where experience and training come into play. A good DPO understands the limitations of each sensor and can make informed decisions to maintain the integrity of the position keeping, ensuring the vessel's safety at all times. Finally, setting thruster strategies and using simulators are essential for proficiency. The DPO can often configure how the DP system uses its thrusters. For instance, they can set a bias to use stern thrusters more than bow thrusters to reduce noise for underwater acoustic systems. Practicing these configurations and emergency scenarios in a simulator is invaluable. Simulators allow DPOs to experience a wide range of failures and environmental conditions in a safe environment. This builds the muscle memory and confidence needed to handle any situation that may arise during real-world offshore operations, turning a good DPO into a great one.